are you? Yesterday, remind me, did we talk about the speed of light?
No.
Okay. All right. So title this speed of light / light speed. And I guess we could actually start off with talking about the speed of sound. How many of you all would describe the speed of sound as being fast? Okay. Yeah, it's fast. Until, what was it, 1947? Chuck Yeager broke the sound barrier in like the XB-1 or whatever it was, right?
Yeah.
They weren't sure if the aircraft would be able to handle it, because as you approach the speed of sound, the aircraft will be buffeted by like a shock wave, right? It's got to break through. It is a physical barrier, okay, not just a speed. If my memory serves, it's something like 730 miles per hour at near sea level. As you go higher, it actually slows down. So it's easier to break the sound barrier at a higher altitude if you're like in a jet, because A, the sound is slower, and there's less air resistance. So as long as you can gobble enough air like a jet can, you're still good. Produce thrust. Anywho, makes me think about the SR-71 Blackbird. It can go how fast? Anybody know? Blackbird, SR-71. Any nerds? Do you know what I'm talking about?
Yeah, 10 or
I
7
think it's like
or something.
Mach 3 is the official release. The official release from the U.S. government's like, yep, it's, well, they say Mach 3 plus. And they say it'll fly up to, how high? 80,000 plus is the last I saw. Have they gone up to 85 now? But it probably, does it say plus? So I've seen a release that's like plus. So there's scuttlebutt, there's rumor that SR-71 could go upwards of Mach 4 and fly at close to 100,000 feet. Basically, here's the thing. They've never released that information. Nothing's official beyond that release. But if you do some kind of like backdoor analytics, you can look up top speeds of like some of the surface-to-air missiles that have been fired at it and how high they can climb and shoot down aircraft, and then realize that the SR-71 was never shot down. Because when they have the little beep beep button that comes on and says you've been fired upon, all they do is put the throttle down and climb, and it can't catch them. Never has. Yes.
It says it was designed to cruise at Mach 3 plus and can reach speeds over greater than Mach 3.2 with 1 1/4 flight reaching Mach 3.5.
Yeah, but it can probably do more. We want to keep some of our secret. Is SR-71 still flying? Not officially. No, it's retired. It's retired, guys. What does that mean? Am I retired?
No.
I am retired from the military. Could they call me back? Yeah. Do you think that they just destroy all of those things? So, no. So there's SR-71s that could be put back into service. The last ones that were still operated were no longer operated by the Air Force, but by the CIA. Yeah. Oh. Cool. Anyway, so speed of sound is fast. 1 Mach is the speed of sound. Mach 2 is twice the speed of sound. Mach 3 is 3 times. You guys get the gist, right? As I'm speaking to you, you all are relatively close to me. And you can see my mouth moving, and the sound matches. Does that make sense? However, if we were far enough away and you could still hear me, it would start to separate, wouldn't it? It would start to be like a bad movie where the dubbing's not quite right. Yeah. So, can anybody give me an example of something happening off in the distance that you can see it happen, but then you don't hear it? You know it made a sound, maybe a loud sound, but you see it happen, and then you have to wait for the sound. Go ahead, everybody. Lightning and thunder, fireworks, lightning and thunder, a gunshot, a plane. Oh yeah, plane's a good one because you're like, I hear it, and how many of you have done this? You hear it and you turn, and you're hearing it where it was, and it's over here now. So now, if it's got contrails, you're like, just trace the contrails and you'll find it, right? Cool. How about this? Similarly to how you turned to see where the sound came from, and it's no longer there. What about objects really far away? How about like Proxima Centauri, our nearest stellar neighbor? Okay, how far away is that? Does anybody know off the top of their head? It's 4.2 light years. Okay, when we look out with with our high-powered, I mean, this is like, you can't see it with like your backyard telescope. Okay, you got to have a pretty high-powered setup. Is the planet where you see it, or the star? It's not there. You're seeing it where it was, just like you heard the jet where it was, not where it is. Does that make sense? It's the same thing. So if we're looking at Proxima Centauri or any other stellar object, we're seeing it where it was when the light left that object. Does that make sense? Okay, so let's pause, hold that thought for a second. The speed of light, if you need to put this in your notes, is 186,000 miles per second. Is that fast?
Yeah.
Yes.
That's on a whole nother level than the speed of sound. This would be like a snail, and this is like the SR-71 Blackbird. Okay, if you want to do that kind of analogy, simile, whatever the heck, an English term that is. How big around is the planet Earth? Do we remember? We did this earlier in the year. We rounded down to 24,000 miles for what we were doing. This time we'll round up to 25. Okay, so around the equator. Now, can light travel in a curve to orbit the Earth? No. Not as far as we know. Light can't do that. Light wants to travel in a straight line. Can it be curved? Yes. By the Earth? No. But we're going to assume, just for this hypothetical, if light were able to travel in an orbit around the Earth, how many times could it go around the Earth in 1 second?
8.
Almost 8. So you took 186,000 divided by 25,000, and you got what, 7.4 something? Okay. So 7 whole times around inside of 1 second. Everybody wrap their head around that. Good? The moon is 237,000 miles from the Earth on average. Go ahead and tell me, how long does it take for light to get from the moon to the Earth? 237,000 miles. If you've got a calculator, all you have to do is divide 237,000 by the speed of light in seconds, and it'll tell you how many seconds it takes to get here. Huh? You all have access to calculators. 1.3? Just over 1.25 seconds. So 1001, and then it's done, right? It's there. So if we had, for instance, if we had astronauts out at about the moon's distance, we've done that before, right? Right, Apollo cruise. Some of them landed, some of them just did laps around it, right? If they're all the way out at that distance, can you imagine that there would be a delay in the radio communications?
Yeah.
Radio is light, yes? Yeah, really long wavelength light. So it's traveling at this speed. So imagine you radio, and as soon as you're done saying your message, it's going to take a second and a half almost to get to Houston. They're going to have to finish hearing it, however long your message was. All that while you're waiting for a response, and then they'll start to say a response. You won't start to get it until another second and a half later. There's a delay. It'd be a little irritating. I wonder if they did training. Like, I wonder if NASA and the astronauts, I wonder if they did training just to, like, get used to having a delay in the communication. You think?
No.
Probably would have been smart to do it if they didn't. Anyway, all right. Light speed versus light year. What's a light year?
Years, the distance of.
Go ahead, Showstran.
So how long light travels in a vacuum for an entire year, like the distance?
The distance. Everybody hear that? A light year is, so if you want to put a definition in your notes, a light year is the distance that light can travel in 1 Earth year through a vacuum.
Say that one more time.
Yes. A light year is the distance light can travel in 1 year. 1 Earth year. So to get that, what would we do? We'd take 186,000 miles per second times 60, right? To get to minutes. Times 60 again to get to hours. Times 24 to get a whole day of light traveling. Times 365 and a quarter, right? To figure out how far it can go in a year. Does anybody want to do that experiment? Go ahead. You got a calculator? Go ahead. 186,000 times 60 times 60 times 24 times 365 and a quarter. Go ahead. When you get it, raise your hand. Don't blurt it out.
Quarter?
Yeah, 365 and a quarter.
I always had it.
You got that leap year every 4 years, right? Why do they call it a leap year if you're adding a day? You'd think you'd have to leap over it if there was a day missing, right?
They call it. So what would they call it?
Maybe it's referring to the fact that that year they have a leap day.
But if it's leap day, wouldn't you be skipping over it?
Yeah.
All right, so I've got several people that did the work. I have several people that have no intention of doing the work because they know other people will do the work for them. Dangerous habit to get in. All right, what do you got, Nelson?
5.87 e to the 12th.
A big number. Good grief. I wonder if you could like convert that
Already did.
to light years. So, because you've got it in miles, right? You've got it in miles. What is a light year? You'd have that many miles in 1 light year. Yeah, you're coming up with your own. We're coming up with our own conversion. So what on earth? What was it again?
5.869713
The E12 is that the scientific notation thing?
Yeah.
So we'd have to like move the decimal a lot.
Like
It'd be a lot of miles.
No.
It's equal to.
It's like e
Mine
after
didn't have the each one.
It didn't?
It's representing the 10 to the
Okay, so you got it up without a decimal, without the scientific notation. I like that better. Anywho, you get the idea. Let me see that. So if I got 3 to a comma, 3 to a comma, that's millions. 3 to a comma, that's so 586, almost 587 billion miles. Is that right?
Let me double check.
Did I do that right?
Yeah.
Let's cheat. Somebody Google how many miles in a light year.
5.88 trillion.
Perfect. Perfect. So the scientific notation you got us ended up being the number of trillion miles. 5.8 trillion miles. Okay. A lot. So earlier we were talking about distance and time. How many light years to the center of the galaxy? Loop it. How many light years to the center of our own galaxy? What'd you get?
26,000 light years away from
26,000 light years away. Okay. So I want you to think about this for a second. If the center of our galaxy, what you guys know what is at the center of our galaxy?
black hole.
A supermassive black hole. Good. The light from our black hole's accretion disk, if it's currently feeding, you guys understand how like a black hole, as material gets close enough, it'd be orbiting very quickly, yes? And that material will form what's known as an accretion disk around the black hole before it falls in beyond the event horizon, at which point it disappears, right? Okay. So it gets really hot. It actually emits light. So we can see the accretion disk of the black hole even if we can't see the black hole itself. Does that make sense? A few years ago, they, for the first time, directly imaged our black hole, the one at the center of our galaxy. But they didn't image it as it appears now. They imaged it as it appeared, or would have been, no, you gave me the answer.
Oh, 26,000 light years ago.
26,000 years ago. So if it's 26,000 light years away, the light got to us 26,000 years later, right? So if scientists were first able to directly observe the black hole and the accretion disk around or whatever, they're seeing it as it was 26,000 years ago. They're not seeing it as it is now. Could it have changed somewhat? I mean, 26,000 years is a blink of an eye when it comes to like stuff of that magnitude. But is it in the same position? Isn't our galaxy moving through space? Now, in relation to certain things, yeah, absolutely, because we're orbiting around the galactic center, yes? Our solar system? Okay, yeah.
Does gravity have a speed?
Gravity doesn't have a speed. Gravity has a certain amount of force, and that's going to, and that would depend on the mass of the objects involved and their proximity to one another. We're going to, don't worry, we'll do the math for that in the spring. Yes.
If they have the images from 20, or well, equivalent to 26,000 years ago, would they be able to make any guesses as to what it looks like now?
Yes. Yes. So if they're continuously imaging, getting image, they can plug that into a computer model and extrapolate forward where do we think the things might be now. Because you can calculate speed, right? If you take two images, it was here, and then this much time later it was here, you know how fast it's going. That makes sense? Good questions. Good questions. Okay. So could we say this for our notes? Could we say this for our notes? The further away you look, in other words, the further an object is away that you see, the further back in time you're looking. Can we say that? Yeah. The farther an object is away, if you're looking at it, you are seeing it not right now. You're seeing it as it was however long ago. The further away it is, the further back in time. And the number of light years is a one-to-one match on how many years ago. Everybody good on that? Okay. Time travel. Is time travel possible?
Yes.
The E equals MC squared and all that Einstein stuff allows for time travel. Anybody ever seen the movie Interstellar?
Yeah.
Okay. So in Interstellar, they deal with, I'm trying to think, at least one type of time travel. We might not think of it that way. It's not so much time travel as it is relative time dilation or time differential. So depending on where you are, time can behave differently, if that makes sense. If you are close to something that's very massive, like a supermassive black hole, time tends to slow down in relation to being further away, which is why in the movie they aged more slowly than the people back in our solar system, right? Where was that station? Wasn't it like around Jupiter or something at the end of the movie? I forget. So that's one way time travel-ish can happen is gravity affects time. Another thing that affects time is speed. You heard this one? So they did an experiment years ago, I don't know when, you'd have to look it up. They took one of these fancy, super precise atomic clock things, and they're identical, and they set them so they're exactly clicking in time with each other, perfectly synchronized. They leave one here on Earth, and they put the other one up in orbit. Well, if an object is in orbit around the Earth, it's got to be going at least 17,000 and change miles per hour, because that's the escape velocity to get away from Earth. Does that make sense? Over, I don't know how long time, but over months or years, whatever, they saw an incremental shift in one clock from the other. In other words, the speed of an object impacts the way it experiences time. Does that make sense? That doesn't make sense to me. I don't have that level of math. Okay, but that's what I've read and seen and whatnot. All right. Are we good on light speed? Are we good on light years? Okay. Moving on then. We are, reminder, we got a quiz tomorrow. My biggest worry is that I've heard several students say, oh yeah, that's the one on water. I got it, that's easy. So, and it might be, but just verify if you haven't checked like this mind map thing or the quiz or the flashcards before tomorrow's quiz. Make sure you glance at it and make sure you're not blindsided, because I'd hate for there to be an overconfidence problem. Does that make sense?
Yeah.
Okay.